Okay,
Kevin?
yeah, ready to go? Okay,
Fire away. Yeah.
okay, good. So I'll try to keep this down to 10 minutes by talking faster than usual. Hope that's, no, I won't. I'll try to do it nicely. So I'm talking now about an instrument suite that we're developing that will perform comprehensive in situ measurements of the composition and microphysical properties of Venus clouds and gases. We've heard earlier this week how important this is to be able to really study the clouds of Venus, what's there, what's in the aerosols. Particularly the aerosols are important because of chemical effects and looking for exotic molecules that may not be found in the atmosphere itself, but could be residing inside the aerosols. So next, please, next slide. So we have the package is comprised of two elements. We have the aerosol mass spectrometer, which we're developing and building at JPL, and then for the the nephelometer, an aerosol counter that's being developed in France at CNRS, and we're going to these together give you both the particle sizes and distributions, and as well as the composition of the aerosols. And this will you can go ahead one slide. So the objectives we talked about this meeting, but let's next slide. We've talked about this meeting, but in the throes of doing a proposal for an advanced mission to Venus, we've come up with these objectives for a mission that we'd like to do, which is a long duration balloon. But this instrument could be used on any kind of vehicle that's in Venus, including probes, because it's very fast and very efficient. So even the probe descending could do a lot of great data measurements very quickly there. Let's back up. So we went forward. Let's go back up the slide again. All right. So there's three major, in terms of a balloon, when you talk about the composition, there's one major goal here, but there's three major sub goals under it. And the sub goals, are to determine the primary photo and thermal chemical pathways. The problem is that we understand the gases somewhat from previous missions, but again, the aerosols are complete unknown, what they're made out of, and particularly aerosols such as sulfuric acid can absorb molecules, and you can sequester molecules away. And then as well, those aerosols can perform their own chemistry. You can have their own little chemical labs, and you can get daughter products and granddaughter products and a whole slew of products out of inside the aerosols, which then can be released to the atmosphere and cause more chemistry. So if we're going to understand everything about this, the different cycles involved in the chemistry of the atmosphere, we need to understand what's in the aerosol. The other thing is, as has been mentioned many times, is the composition of the UV absorber. We think as a byproduct, just understanding what's inside aerosols, we will find out what the absorber is. And then we'll assess potential habitability, including, sulfuric acid acidity. There's still a question about what the acidity of the aerosols are, and there might not be as high acidity as theories out there. And we could verify that. We can actually directly measure these aerosols and see what the acidity is. That's just one aspect. There's several other things, like you said before, finding trace gases that are probably interesting. Okay, next slide, please. And so the chemical pathways are shown here, famous Fegley diagram. Again, heterogeneous chemistry is the main deal, and that's shown in the next slide. Next slide. And there we have what's happening is you have gases. This is a process called uptake. You have HCl and HF are two primary constituents that these aerosols can absorb, and depends dramatically in altitude. So we show a little diagram there. 55 kilometers, relatively little goes in, and 70 kilometers, a lot more goes in. It actually likes colder temperatures and lower, lower composite acidities. So that's what you get, we think, as a function of altitude. So you have variations, and it goes in there. And then the next slide shows that out of these things, you can get all sorts of weird molecules. Out of HCl, you get what's chlorosulfonic acid, and you get fluorosulfonic acids. And then those guys can actually then generate on the right side even more daughter products. So, and some of these are UV absorbing. So it's the interesting part of the UV absorbing question to see if any of those products are what's semi-responsible. Probably not totally responsible, but it could contribute to the UV absorbing of these particles. Okay, next slide. And then phosphine. H2SO4 readily absorbs phosphine. And so we already know phosphine has a small lifetime in the atmosphere of Venus due to solar radiation and other effects. But one other effect of phosphine encounters sulfuric acid, it gets absorbed, and then it creates other stuff. A lot of phosphoric and phosphorus acids get created. And what's interesting on the right side, you can see that actually, that once you create phosphorus acids, it actually regenerates a phosphine, but it's not a net generator. It takes four the whole thing takes 4 phosphines to get one phosphine back. So it's really a phosphine sink, but it's one way you can create a phosphine molecule if you want, but it doesn't solve the problem of how come there's phosphine there. All right, but this is very interesting chemistry that we need to look at. Okay, next slide. And I'm pointing out here that the only gas that has phosphine in it in this range, in the temperate zone that we're looking at here in the clouds, the only gas is phosphine. The rest of the phosphoric products are all liquids and maybe solids. But if you're going to try to study what's going on in the clouds when it comes to phosphorus species, you really do need to zap them and see what they're made out of. Okay, so that's what this instrument will do. Okay, go ahead. Next slide. And then we just talked about UV absorber. It's an outstanding question what it is. Lots of theories out there. You know, iron chloride's been out there for a long time, and other ones, or might be some we don't know about, like I mentioned, you know, result of these sulfonic acids. But anyway, we could easily nail that down, really, you know, see what's going on with that. Okay, next slide. And then the whole hypothesis of habitability, Sarah Seeger's famous, it's becoming famous. So a cycle here shown on the left where things vary with altitude, and you might have dried out spores down low, and you have life giving spores up high. So things change, and this is the kind of thing that if you had a mission that went up and down in the atmosphere, you could sample that and see if it's really true. As well as you can do day and night. And a lot of these kinds of processes will be, you know, when the sun's up, things will happen, like I mentioned before, phosphine will get destroyed. But if you go at nighttime, the phosphine is likely to build up, not be more. It's not going to be destroyed by sunlight, at least. And so looking at those cycles would be a fantastic thing to do, and this instrument could do that. Okay, next slide. And this is just to show we've done some modeling of what it is, how much HCl gets sopped up by H2SO4, and I've circled there 55 kilometers, where we're at about 0.4 parts per billion, and so we sorry, it's the wrong thing. Anyway, let's come to the left. So it's two parts per billion. So we made it a goal for this instrument, and we're so far achieving it, that we can get 2 parts per billion. That's per H2SO4 compared to H2SO4. 2 parts per billion in 300 seconds. That's 5 minutes. So in 5 minutes, we think we can get to that with a 20% error on that. And we're shooting for that, and so far it looks like we'll probably make that. So that'll be the goal. That's sort of setting the goal of how good this instrument's going to be. Okay, next slide. And so here we show how the mass spectrometer works. So we have 2 channels. One does aerosol mode, which we've been emphasizing. The other channel does gas mode. So we do it differently. And on the diagram, the lower left, the aerosol mode is sort of off to the left, and the gas mode is coming up from the bottom. So you can go back and forth between aerosols and gases. And one thing you want to do is you know, measure gases for a little while, typically 15 minutes, and then do aerosol for 15 minutes on a balloon. If you're on a probe, you could do it a lot faster. But anyway, that's what we would do. And so you can go back and forth, and with all the cleaning cycles involved, you can do that in about 15-minute scales. So that's what it's doing. And the aerosol advanced aerosol separator, it's an advanced device we're developing JPL, and what you have to do is you got to get rid of the gases. You know, at least, you know, only 1 part in a million of a sample is going to be aerosols. The other parts are all gases. We want to get rid of that, and we want to do better than 10 to the 6. So we're going about 10 to the 8 or so, and we can feed that then into a vaporizer. Once you have your nice little bullets of aerosols, you then feed them into a vaporizer. It goes up to 600 degrees Celsius, and you zap them, turn them into gases, and then you measure what's in those aerosols, and then you go take a gas sample later on and compare that. And so you can do this nice comparison and see what's really going on. So in terms of, by the way, in terms of you know, trace gases or trace materials inside the aerosols compared to the bulk atmosphere of CO2, I mean, we're talking about parts in trillions here, and that if you do relative scales that way between the outside environment and what's inside the aerosol. All right, so let's go on the next slide.
Kevin, I think you have to wrap up here.
Really? Okay, next slide, really quick. Next slide. Okay, so I just mentioned all these things, 2 parts per billion. We go from 202 to 150 AMU. We have 16,000 channels, and it takes 0.05 seconds to get a sample. And signal to noise you want to improve, so you do it lots of times. But the point is, we get, you know, we see all these channels, and if we want, we can go to high resolution mode by binning things and changing electronics a little bit. So we can get down to you know, very small AMUs. We can get down to 0.01, even less AMUs of sampling. Okay, next channel, next slide. And this shows a panoply of things that we can measure. And I'm not going to talk about it anymore, but we can do all these different molecules and anything else that people come up with. Next slide, please. And then this is the LOAC. It's got 2 channels, basic kind of we're going with a low cost one now. We might expand it later and get more channels and start talking about doing phase functions. But so far, we think with this, we can particle size and see the distribution of particles and their sizes. And next slide, please. Last slide, I think it is. Yeah. And so this is good for probes and for aerial platforms. And I'll just leave this slide up and that's it. And we're going to begin testing of this summer, it looks like, using the new facility that we're building at JPL, an aerosol facility that will create aerosols, and then we can use this instrument and test it and make sure we're getting things working right. So that, I'll
Hey,
stop
thanks,
there.
Kevin.
Yep.